Hi, I'm Lloyd, engineer at Embelton. Today I'm going to discuss a simple but important quantity in vibration isolation, static deflection. In a mechanical services specification, the anti-vibration mounting requirements will typically be given in terms of a static deflection that needs to be achieved for each major plant item. Provided that's met, then performance is taken care of. But what is static deflection, and how does that determine what your isolation performance is? Static deflection is the amount the isolating element has travelled or compressed from its free height onto the mass that it's supporting. So it's the ratio of stiffness to mass. And this is the key because it can tell us what the natural frequency of oscillation is, which is the fundamental property determining isolation performance. So for a quick demonstration, here we have an 18mm compressed fibre cement sheet on Embelton XS springs. I'll give it an excitation. If you want to know what the natural frequency is, you can see it can be difficult to time. We could work out what the weight of the cement sheet is and get stiffness data for the spring, but if you're working with an older piece of plant, the mass data might not be readily available. We could get an accelerometer, which will give us frequency domain data. Not everyone has access to that either though. It's much simpler just to measure the static deflection on the mount, which immediately tells us what the stiffness to mass ratio is. So if I know that the free height of these springs is 82mm, I can take my tape measure, measure the deflected height, which comes out at about 75mm. So that tells me that I've got 7mm of static deflection. I can put that into my natural frequency equation, and that tells me that my natural frequency is 6 Hz. If I add more mass, 25 kilograms, I can see that my platform was visibly deflected further. Retaking my static deflection measurement, I'm now getting about 20mm, which is 3.5 Hz when we plug it into our natural frequency equation. Side by side, I give this an excitation. We can see that with the mass on, it's noticeably slowed down. We've got a longer period for the same input force, which means that the platform is undergoing a lower acceleration as it changes speed during oscillation, which translates to a lower force reacted at the structure. If the speed of our rotating machinery on top of the platform matches the natural frequency, then that's what a resonance occurrence is. And we only start isolating when the speed is significantly higher than this. In fact, the higher your speed of your rotating machinery relative to your isolator frequency, the better your theoretical isolation performance. So the operating speed of the plant will be one of the major factors in how much static deflection is deemed acceptable. So natural frequency is what we ultimately want to determine, and the static deflection represents a simple way of calculating this so that we can select appropriate springs. Should note, however, this only works with the assumption of linear stiffness isolators. For non-linear springs and most rubber mounts, static deflection isn't a really accurate way to determine the natural frequency in isolation performance. That's it. Thanks for watching. See you next time.